We're continuing to look at real-world situations of linear programming, and we're given the following situation. A company produces 3 different types of widgets that take the same amount of time to manufacture. After labor and material costs, widget A sells for a profit of $3 each, widget B sells for a profit of $5 each, and widget C sells for a profit of $4 each. The company has historically sold at least 3 times more of widget A than widget B, and never more than 200 of widget C. If this company can produce 1,000 total widgets and product sales follow these historical patterns, what quantity of each widget should be manufactured to achieve a maximum profit? Okay, this is a very good industrial manufacturing situation here. So let's go ahead and define a few variables. We have 3 widgets, widget A, B, and C, and we want to know what amount of each quantity of widgets should be produced to maximize our profits. So let's go ahead and define our variables in terms of our number of widgets produced. So let's go ahead and let X equal the number of widgets A produced. This is our first one, widgets A, and they're produced at a profit of $3 each. So this is produced at a profit of $3 each. Okay. Next we have Y. Let's define our variable Y, and our next widget is widget B. So this is going to be the number of widgets B produced. And widget B is produced at a profit of $5 each. Profit of $5 each. And now we have a third widget called widget C, so we're going to need some sort of expression relating the variables X and Y to the total amount of widgets produced. And if you viewed the previous application on linear programming, it's actually going to look very similar. We know that this company produces 1,000 total widgets, and that's broken up over 3 different types. So we can say that 1,000 minus X plus Y, which is widgets A and B, are going to equal the amount of widget C produced. So we have 1,000 total, so if we take away the amount, or we subtract the amount of widgets A and B produced, well, widget C is going to comprise the rest of the 1,000 widgets produced. So it kind of makes sense. We just got to use a little intuition. So we have 1,000 minus X plus Y, and this is going to equal the number of widgets C produced. And this is at a $4 profit. So we're making a $4 profit off of each widget C produced. Each. Okay, so we need to define one more variable. And what do we want to find here? We're trying to find the quantity of each widget that should be manufactured to achieve a maximum profit. So we want a maximum profit. So let's define our variable C as the company's total profit. And this variable Z is actually what we want to maximize. So we need to write some sort of optimization equations that we can maximize using these given variables and the given constraints that we'll define next. So let's go ahead and find an optimization equation. The total profit for the company is going to be found by adding the total amounts of widgets A produced times the profit of each of them, plus the total amount of widgets B produced times the profit for each of them, and plus the total amount of widget C produced times the total profit for each one of them. So we can say, let's go ahead and write an equation. We can say that Z, our total profit for the company, equals 3 times X, because widget A is produced at a $3 profit for each one, plus 5 times Y, because we're getting a $5 profit for each widget B produced, plus $4 times this expression, because this expression defines the number of widget C produced. So 4 is going to be multiplied by this entire expression. X plus Y. All right, so now we can go ahead and simplify this out. So we have 3x plus 5y plus, let's go ahead and rewrite 4 and distribute this minus sign inside the parentheses. So we have 1,000 minus x minus y. All right, let's go ahead and further simplify. So we have 3x plus 5y, and we can go ahead and distribute this 4 into the parentheses. So we have 4,000 minus plus and a negative will give us a negative 4x minus 4y. We can go ahead and combine like terms. So we have 3x minus 4x, or excuse me, let's go ahead and write 4,000 since it's a positive number. 3x minus 4x is just minus 1x, and 5y minus 4y gives us a positive y. So this is our optimization equation that we want to maximize, 4,000 minus x plus y. Once we maximize this optimization equation, we'll get the maximum profits for each situation. We want to find out how many of each widget we want to manufacture to maximize this profit equation. So let's go ahead and list some constraints. We do know some constraints, so let's go ahead and put them in numerical form. So we know first that the company sells at least 3 times more of widget A than widget B. So our first constraint is going to be x is widget A, so x is going to be greater than or equal to 3y, because we're going to sell at least 3 times more of widget A than widget B. So we're going to sell greater than or equal to, x is greater than or equal to 3y, which we can go ahead and solve this for y, and say that y is less than or equal to 1 over 3 times x. So this is our first constraint. All right, what's our next one? Well, we know the company never sells more than 200 of widget C. Widget C is defined by this expression, the total amount of widget C produced. So we can say that 1,000 minus x plus y is less than or equal to 200, because we never produce more than 200 of widget C, and this is the expression to define the number of widget C produced. So we can go ahead, and if we go ahead and solve this for y, that'll give us y is greater than or equal to 800 minus x. Okay, and this is our second constraint. All right, let's go ahead and find a couple more, because we actually do have 2 that are actually just understood, just because this is a real world situation describing real quantities. We know that x is going to be greater than or equal to 0, because we can't produce a negative number of widget A. So we're either going to be producing 0 widgets of A, or we're going to be producing a positive number of A. So this is another constraint. We're also going to have y is greater than or equal to 0, because we can't produce a negative number of widget B. Okay, so these are actually just using a little intuition to come up with these constraints. They're not spelled out, but we can't produce a negative number of these widgets. All right, and also we can't produce a negative number of widget C. So that's going to be our 1, 2, 3, 4, 5th constraint. So we're going to have 1,000 minus 1,000, there it is, minus x plus y, and that's going to be greater than or equal to 0. And if we go ahead and simplify this out, this is going to be in slope-intercept form. Y is less than or equal to 1,000 minus x. So here is our 5th constraint. All right, so we have our optimization equation that we want to maximize, and we have 5 constraints here. So we're almost out of time, so let's go ahead and pick this up in the next video. We have our optimization equation and our restraints, so in the next section, or in the next video, we're going to actually graph these constraints, and we'll come up with a feasibility region, and we know that the corners of that feasibility region produces 4 systems of equations, and we need to solve each so we can actually maximize this optimization equation. So I'll see you in the next video.